Well, there, and welcome back. So, we have started again discussing second order system with the example of mass spring model. So, you see, we have shown you in my earlier lecture how to actually, this is the equation, okay, dynamic equation, and just recapitulation a little bit. And this is the natural frequency omega equals to root over of k by m, okay, and the solutions were actually x equals to x dot 0 divided by omega and sine omega t plus x0 cos omega t, because our trial solution was, if you remember, a sine omega t plus b cosine omega t. This is second order system, and that's why two constants are there. It's very interesting to see. You see, this is actually the total solution is x1, x2, and this trial solution we got intuitively. Just if I perturb means, zero force, very small duration. It is working just like this. Okay. If I perturb, then how it will oscillate? This is also called free oscillation or free vibration. That means no external force is there which is acting on the system. Okay, and I told you why gravity will not be playing any role in free oscillation, because you can easily imagine the same mass spring system like this. Okay, and I can just perturb in this direction, and then it will oscillate back and forth like that. Okay, and the motion will be same as what it will if it is hanging on the vertical hinge. Okay, only difference is depending on the g. Okay, the mean position of equilibrium about which it will oscillate will be different. Okay, that's it. Now you see, since it is a linear, so that's why it is second order linear differential equation. So we are considering that the system is linear. That's why say I have a solution intuitively, a sin omega t, another solution b cosine omega t, and we can just merge them together. Okay, we could have done it also like this. Okay, who told you that it has to be plus? This could be also multiplication, but it will not happen because we are considering a linear differential, second order differential equation. Well, so far so good. So this is the solution, and these were our boundary condition or initial condition. That means at t equal to 0, the velocity was x naught dot. Okay, at t equal to 0, the position was, or displacement was, x naught. Okay, and our solution was x equals to capital X sine omega t plus phi, where the x is amplitude of oscillation. Okay, is equals to this. Okay, x naught dot divided by omega square plus x naught square. And tan phi incidentally was, and this using separation of variable principle, I have shown you how to, in my earlier lecture, how to get the, it's very clean, how to get the solution. Okay, so from there you can also calculate time period. Okay, because it is oscillating back and forth. So when it will come to the same phase, how much time it will take is called time period. Okay, that oscillation will be in same phase. So tau equal to, if the total angle is 2 pi and omega is actually angular frequency, which is omega equal to the unit is radian per second. Okay, so time period will be in second. Okay, and then frequency will be how many oscillation has taken place per unit time. So 1 by time period, which is equals to omega by 2 pi, that is the hertz. Okay, also you see, using this, the implicitly, if I even if I do not know the system parameter k and m, okay, so implicitly I can just hang a mass and only measure with a scale that what is the displacement taking place. If I can measure that, and if I know the acceleration due to gravity at that particular place, then if I know only this, I can also calculate the natural frequency of that system, which is by definition k by root over of k by m equals to root over of, you see, I have imported a g divided by mg by k. So that same thing I am writing in this form. And now the gravity is important, right? So mg is a total force which is acting on the system. So, and by definition, what is deflection of the spring equal to, what is the stiffness of the spring definition? Force divided by deflection. Okay, so deflection equals to force divided by k. Force is here mg, so mg, that is the force acting here. We are considering no other force, only gravity. So mg by k equals to delta. So this is your natural frequency. So natural frequency can be computed using this. Natural frequency explicitly can be computed using knowing both the system parameter. Okay. So far so good. So from 2 and 3, what we can do, you see, now we would like to derive the velocity and acceleration relation. Okay, so I am differentiating 2, okay, and getting this very simple. Sin omega t, that's omega is coming, cos omega t minus x0 omega sin omega t. So omega cancels out. Then this is the from 2, right? And we are writing, and this is equals to also this. Okay, so from 3, so from 3 we can just write down this. Okay, so this is x omega, x is amplitude of oscillation, omega. Okay, so equals to sin omega t plus phi plus pi by 2. Okay, so you see I have written this in this form with an intention. Okay, later on when pictorially we'll show you the plot. X actually solution means x versus t, x dot versus t, x double dot versus t. Well, t in place of t we can also we will do that omega t, because that will simplify our this plot. Okay, because omega is constant. Okay, so this is equals to x dot cosine omega t plus phi. So here if I put x dot equals to x omega, we are calling this amplitude of velocity. So amplitude of velocity, x dot, okay, velocity equals to amplitude of velocity and cosine of that term. And this is, if I consider this as displacement versus t, velocity versus t actually is actually leading by pi by 2 or 90 degree. Similarly, we can also calculate x double dot. So again, I am reproducing from my earlier expression. So these are all we are reproducing, 2, 3, and 7. 2, 3, and we are again differentiating this with respect to time. So we are getting this expression, okay, minus. So that is giving you x omega square sine omega t plus phi. Again, we are writing this minus. Now it will be plus, because we have added pi term here, all sine 10. So this is third quadrant, sine is negative. So we have written this with a purpose. What is that purpose? You see, and meanwhile you see if I write this by putting, so this is the amplitude of oscillation for acceleration. So what observation we are doing here? Velocity omega times the displacement and leads it by 90 degree, you see. leads it by 90 degree. And the acceleration is omega square times the displacement and leads it by pi or 180 degree. Okay, so now we can plot displacement and we can actually plot this. Okay, so this is our displacement versus omega t. Okay, this is velocity versus omega t, and this is acceleration versus omega t. So if we plot, then we are seeing that this is the phi phase, okay, and this is the initial, because I'll have to, so I cannot put it like that, then x0 will be 0, right? So that in general way I am writing the solution, that's why I have to show x naught, and then there will be a phase, okay? So that is the phase angle phi, and this is amplitude of oscillation. So simply I am plotting this, I am plotting this, I am plotting this, and this, right? So these are the thing I am plotting, and we are getting pictorially the displacement versus t, x dot versus t, x double dot versus t. So solutions of the differential equation means you are getting all this. Okay. Now coming back, so this is very interesting observation, and then as I told you that there is a number of method for solving differential equation. I will show you another method, okay, which is widely used, okay, is actually x equals to c. C is a constant, e to the power exponential term st, okay. C is a constant, e to the power st. C is e is exponential. So this is a trial solution. So x naught equals to c s e to the power st. X then again differentiate again, x double dot equal to c s square e to the power st. So that is giving you c s square this actually. So if this is a trial solution, it has to satisfy this. So that's why I have figured out this, and we are putting them. So s square plus omega square equal to 0, and then this is the characteristic solution, characteristic equation, and the this is, you see, it's no more a differential equation. This is algebraic in nature. So s is a parameter, okay, and very interesting. We will actually s plot. We will see in the Argon diagram. So two solutions will be plus minus I omega. So the total solution will be x equals to c1 e to the power I omega t plus c2 e to the power minus I omega t. Again, it is very, very interesting observation why this plus sign is coming, because we are considering second order linear differential equation. So I am getting solution for one root, okay, solution for another root, and the total solution will be solution x1, x2, and they can be added together because we are considering second order. This is second order linear differential equation. Had it not been linear, then we would not be able to write this is the solution, okay. So this is very important observation, okay. I think it is clear, right? So I have a solution x1 corresponding to h1, which is equals to c1 e to the power I omega t. Another solution x2, c2 e to the power minus I omega t. And I could just write x equals to x1 plus x2 because it is a linear system. Now, by that's Euler relation is there is a very interesting relation known as Euler relation, heavily used in control. E to the power I theta equals to cos theta plus I sin theta. So x equals to C1. So now, okay, so we are now writing C1, okay, C1 e to the power I omega t. So you see, you'll have to write I omega t equals to cosine omega t plus I sine omega t, and then e to the power minus I omega t equals to cosine cos of minus theta equal to cos theta cos t minus I sine omega t, blah blah blah, and then just after simplification, okay, after simplification you will get what we have written here. Just you better do this, don't jump the steps. So C1 cosine omega t plus I sine omega t plus C2 cosine omega t minus I sine omega t. So a little bit algebra. I of I equals to root over of minus 1. It is a complex quantity, okay. So I equals to, so I times C1 minus C2 sine omega t plus C1 plus C2 cosine omega t. So in place of this I am writing A sine omega t. In place of this I am writing B cosine omega t, where C1 equals to A plus IB, C2 equal to A minus IB. So so this we are considering, these are constant, right? And we are considering constant to be conjugate, and the reason I will tell you, because our roots are conjugate, okay, plus I omega minus I omega, okay, their magnitude is same. So we can consider the constant attached with the root as a conjugate quantity also. The reason is why? Because A and B will be real quantity. I C1 minus C2 equals to I into 2IB, you see. Just C1 plus C2 equal to 2A, and C1 minus C2 will be, so 2IB, okay. So 2IB times I will be minus 2B equals to A. So C1 plus C2 equals to 2A equals to B, and this, so you now know A, B, so they are constant, real constant, and this is very interesting. This is called Argon diagram, and this kind of system can be represented using Argon diagram, right? Or sometimes we call it S plot. What is Argon diagram? Perhaps you know. If you do not know, then this is a particular diagram where which is drawn in case of control. This is very interesting, and plotted using two axes, orthogonal axes. One is real axis, another is imaginary axis. Okay, so I equals to root over of minus 1, imaginary axis and real axis. So this is the reason. So of what we see, the roots are completely imaginary and purely imaginary in nature. And what does it mean? It's not something you can only you can imagine. No, it has real consequences. Anything which has a imaginary part has oscillation. Why? Because you see, that is it. Only that that is the physical implication of a root being imaginary in nature. So here, because e to the power I theta equal to cos theta plus I sin theta, so the this can also be written cos theta I sin theta. So that means it is the system response will be oscillatory in nature, okay, and purely oscillatory in nature, okay, because the roots are purely on imaginary axis. Had there been roots like this, that means it has a real component, okay. So this is a real component, this imaginary component, okay. So this is real, this is imaginary component. Then what will be the implications? All the kind of things we will study. That's why this is very, very important. When we will study control, and as such, when you will study mass spring damper system, right after this, you will see this is very convenient. This trial solution, this kind of trial solution is widely used and very convenient. So again, we are making trial, and with a little bit thinking ahead, that I know it is Euler's relation. I know the nature of the oscillation is oscillatory in nature. Okay, and that's why this kind of trial solution I will consider, and I will get this kind of solution. Okay, and this is very, very interesting. Please remember, we will use it afterwards also. Now, it need not be only the technique which you have learnt need not be only applied for this kind of linear motion, okay, in this single degrees of freedom system, right, in this x direction. It could be oscillatory also in nature. So if it is oscillatory in nature, how to solve such kind of differential equation? You see, this is example. This is a pendulum. Okay, we are not telling it is a simple pendulum right now. Okay, so it's a pendulum, and say this is hanging from this point called hinge point from the ceiling. Okay, so it's a pendulum bob having mass m, and it is acted on gravitational force. Okay, g is acceleration due to gravity. What is the force acting? Mg. And very interestingly, when I told that mass spring system, in mass spring system, g has no role to play. Here in angular oscillation, okay, that was a linear oscillation. In angular oscillation, interestingly, the gravity plays a part. If there is no gravity, there will be no oscillation. So this is interesting point I want you to note. So you see, now same old story. This is my direction of motion, dom. I am considering this direction of motion. You can consider this direction of motion, hardly matters, same. Okay, and say at any instant of time it has been perturbed like this, perturbed, small torque I have applied about this, and then it will oscillate, and in that process of oscillation it has moved up to this. Okay, so what are the forces acting on this bob? Okay, so I can draw a free body diagram. Okay, I can draw a free body diagram. Just cut it, and then what are the forces? This is the tension. Okay, this is mg. Okay, and what else? You see, according to D'Alembert principle, again I am using D'Alembert principle, the inertia time, that will be a inertial torque. There it was inertial force, here it will be inertial torque, and there it was mass time acceleration, linear acceleration. Here it will be inertia type angular acceleration. Okay, so this is the inertial torque which is acting on this. Okay, and under this forces, the system, the pendulum, is in virtual static state. So all the static equilibrium condition, that is D'Alembert principle, right? So if we apply inertial torque in the direction opposite to the direction of motion, sorry, I have shown wrongly direction of motion, opposite to the direction of motion, then the system will be in virtual static state. And then all the virtual equilibrium condition you can put. So I will put here. So taking moment of all the forces about the hinge point O, then what you will get? See, this is L. So this is L sin theta. Okay, and then what you can write? So I, this is I. So this is in this direction. This is inertial torque, I theta double dot. The moment of this force about this in this direction. Okay, so both are clockwise direction. This one and this one. So plus mg L sin theta equal to 0. Okay, so just divided by ml square. Okay, so that is equals to theta double dot plus g by L sin theta equal to 0. And then you see, this is not a linear system. Eh? Why? Because this is a transcendental term sin theta, which is a series. Okay, so sin theta equal to theta minus theta cube by factorial 3 plus theta to the power 5 factorial 5 minus theta to the power 7 factorial 7 plus theta to the power 9 by factorial 9 minus, like that. You can continue minus. So who is going to solve this kind of, so this is equals to, okay, so this is equals to 0. This is the, sorry, 0 is missing. So this is the equation, right? It's extremely difficult to solve. Okay. So what we do? So up to this, it is a pendulum equation, okay? Dynamic equation of the pendulum, which is very difficult to solve. Solve means what? Again, we want theta versus omega t, okay? And then plot, we want theta dot versus omega t, theta double dot versus omega t, etc., etc. For that, I will have to solve this equation, right? And this is not solvable, definitely. Okay, so what we will do? We will, this nonlinear equation, we will try to linearize. How? By approximation. You see, we will make an assumption that theta is so small, less than 4 degrees, so that sin theta is almost equal to theta. Okay, but if I do that assumption, then this equation, this differential equation is taking this safe, g by L theta equal to 0. So this is again second ordered linear differential equation. The solution will be exactly same as mx double dot, okay, x double dot plus omega square x equal to 0. So this was, x was in linear motion, theta is in angular motion. That's the only difference, but same technology which you have studied earlier will be valid here. And of course, omega equals root over of L by G. So this assumption is very, very important. And then, you see, we engineers, we always do this kind of thing for our convenience. But the system is, actual system is not like this, right? It's a pendulum. It's not a simple pendulum. So this is a solution of, this is a differential equation for simple pendulum. Sin theta equal to theta. Theta is very small, this with this assumption. Otherwise, this is the equation of motion for a pendulum. And what is the benefit? Benefit is easily solvable. What is the disadvantage? Disadvantage is this t frequency, time period, frequency, all t equal to, you see, 2 pi root over of L by L by G. Yeah? So this is, so this is G by L, sorry. So omega equal to, this is G by L. So omega is equal to this, that is, this is omega square. G by L equals to G by L equals to omega square. Sorry about that. Okay. So t equal to 2 pi by omega. So 2 pi root over L by G you are getting from this. So this is corresponding to the simple pendulum. Now suppose this is a time period. Now suppose you are taking a ball pendulum bob, which is acting as a pendulum bob, and from your some ceiling you are hanging it with a string, and then you are oscillating it violently. Okay, and you are thinking that this is the solution. So time period will be t equal to 2 pi root over L by G. So you know L, you know G, and time period will be 2 pi root over L by G. You calculate, okay, and you will see that when it is oscillating violently, means theta is large, there will be huge difference between actual. So with a stopwatch you can figure out the time period, right? So bob is oscillating, and when it is hitting the same place, you can just with a mobile phone stopwatch is there, you can calculate time period. And same time period you can calculate from this formula. And you will see there will be huge difference because you are using the wrong solution. Theta is very large. So this solution is no more valid. So this thing you'll have to understand. And so in sometimes we do all kind of linearization, but caution should be there that system should be model should be actual related to the actual system. Okay. So this I wanted to tell you. Okay. So with this we are not going further detail because it's same as mass spring system. So oscillation will be like this. Okay. The solution will be exactly like this. Okay. Now next day we'll talk about forced oscillation. That means if same mass spring system is excited by continuously excited, it's no more zero, right? Continuously excited by an external force, say sinusoidal force, it could be anything. Then again this will be my differential equation, and how to solve this kind of differential equation we'll talk about that. There will be two solutions, one is complementary solution, function, another is particular solution. And in this context we will study two very, very important phenomena. One is called resonance, another is called beating, by solving this type of differential equation. Very interesting. So stay tuned. Till then, stay safe and bye-bye.